Hello, linear algebra students. I had a question about problem 2 of this exercise set from a student, and there must be other students with the same question, so let's talk about it. It's basically about this problem. We have to prove the equivalence of two different expressions of the dot product. The component expression a1b1 plus a2b2, multiply the x-coordinate and y-coordinates together and then adding them up, versus the trigonometry or geometry expression, the length of vector v times length of vector w times cosine of theta, where the angle theta is the angle between the two vectors. In general, as a matter of fact, we have these two expressions. And this time I'm using the double absolute value notation, and that's because we are in 3000 level course now. So single absolute value is used for just one-dimensional case when you have scalars, like real numbers, in that case absolute values are used, or complex numbers, in that case we call those modulus. Anyway, for higher dimensional we use double absolute values. So this is the length of v, and this is length of w times cosine of theta, exactly the same as the right hand side, except that we are using a little bit different notation for higher level course. Now this one is indeed much higher level because we are dealing with n-dimensional case. So a1, a2, all the way up to an, scalar product, b1, b2, all the way up to bn. How do you calculate those? Multiply each component together, a1, b1, a2, b2, a3, b3, all the way up to an, bn, and then add them all up. So the component expression versus geometry expression. They're equivalent, and we have to prove it. How do you do that? Well, here's the hint I gave you. As a matter of fact, no. This one I gave you. The right-hand side, the second one, I withheld. So let's look at the first one. First one I already gave you. The second one, that's the purpose of all this. So, all right, let's talk about the second picture here. From the second picture, let's associate this into the law of cosines here. Capital A, capital B, and capital C as the vertices of this triangle, and small a will be the opposite, so vector v, or the length of vector v, and small b will be the length of vector w, and small c will be the opposite of capital C, the length of this dotted line segment. And then from the laws of cosines, c squared is equal to a squared plus b squared minus 2ab cosine of c. We can express all these in vector forms like we did in the right hand side. Let's see. Cosine of theta, that's angle c, so that's green. And then small a, that's capital A, that's the opposite. Small a is the length of vector v, so this blue, and blue, a corresponds to size of vector v and size of vector v like these. And then size of vector w corresponds to small b, and I'm color coding those in red. Now the association is complete. The final question, what is small c? Express this small c in terms of vectors v and w, and then from that point on it's going to be easy. And these 2.1, 2.2, 2.3, those are actually walking you through this, and then in the end you're going to get the proof. And remark 2.4, I'm going to leave this to everybody as a matter of fact. Can you extend exactly the same idea over to n-dimensional case? Yes, indeed. It's not difficult at all. And then if you do that, you're going to get the second expression. What kind of picture do I use? The same picture. Instead of coordinate axes, these are going to be tilted in terms of three-dimensional coordinate axis or maybe even higher. So no coordinate axis. In that case, it's going to be this picture. And we have exactly the same 2D geometry, same laws of cosines, except that the norm or the absolute value, the lengths of vectors v and w, will be calculated through n-dimensional Pythagorean. Good luck, everybody.